Hello, my name is Markus Pomper and I'm a professor of mathematics at Indiana University East. The purpose of this video is to explain what an equivalence relation is and how an equivalence relation can be used in order to sort objects by a given characteristic. And we'll use geometric shapes of various colors and sizes in our illustration. Let us suppose that we have a set A, and the elements of this set A are represented here by various geometric shapes, figures of various shapes and sizes and colors. We have squares, we have triangles, we have circles, we have hexagons, and they come in sizes as large, as small, and as medium. And they come in various colors, like green and red and blue and even some purple ones. Of course, we can sort these objects according to various characteristics. So, for example, we could sort them all by color. So that way all the red objects are grouped together, all the blue objects are grouped together, and so on. That is one way of sorting those objects by a characteristic. Namely, we sort all those objects in the same class that have the same color. Now let's do it by size. Here we group all the large ones together, all the medium ones together, and all the small ones together. And finally we could, if we're so inclined, sort those objects by shape. So all the round ones go together, all the triangles go together, and so on. Again, we managed to sort our objects according to a certain characteristic, this time by shape. And our equivalence relations will allow us to express in mathematical terms a way to express that objects have shared characteristics. And we will be able to sort those according to this characteristic. Now let's have a look at equivalence relations and what their definition is. So an equivalence relation on a set A is a relation that has three properties, namely that it is reflexive, symmetric, and transitive. So you can remember this by the letters R, S, and T. And we will now explore what these properties mean and how they will help us sorting objects by certain properties, such as shape. In order to do this, let's introduce a new relation R. And this relation R will express that two objects are related if and only if they have the same shape. So for example, a green small round object is related to a large purple round objects because they're both round, they have the same shape. On the other hand, a green square object is not related to a green hexagonal object because the two don't have the same shape. We will now convince ourselves that this relation is an equivalence relation, and we will begin by verifying that it is reflexive. Our relation is reflexive because each object has the same shape as itself. So for example, a round green object is related to itself because it has the same shape as, well, itself. And what we need to emphasize here, however, is that reflexivity is a property of all the objects of our set, not just a single one. So we need to observe that every element in our set is related to itself. In this case, this means every element of our set has the same shape as itself. Now let's see why our relation is symmetric. The reason for this is as follows. Let's suppose that we have an object X that has the same shape as a second object Y. We would express that in mathematical terms as writing that X are Y, or X is R related to Y. But then it is also true that that second object, Y, has the same shape as the first one, namely X, or mathematically speaking, Y is R related to X. So symmetry means that if x is r related to y, then it follows that y is r related to x. And now let's go on to transitivity and see why our relation is transitive. This is because if one object, let's call it x, has the same shape as a second object, say y, or mathematically speaking, x is r related to y, and if furthermore this object y has the same shape as a third object, say z, or mathematically speaking, y is r related to z, then it must also be the case that the first object, x, has the same shape as the third object, z, or x is r related to z. And again, transitivity is not a property that just three objects possess, but is a property that applies to all possible combinations of three objects in our set. So, because we have seen that our relation, being the same shape as, is reflexive, symmetric, and transitive, we conclude that our relation is an equivalence relation. Now let's see how having an equivalence relation can help us sort objects by a common property. We'll begin by looking at one single object, such as this object x here. And we will now create a set. This set will be a subset of our original set A. And in this subset, we will include all those elements, all those objects that are related to x. That means we include in our subset all those objects y for which the relation x r y holds. We can use set builder notation to denote this as a set by writing the set of all objects y for which x is r related to y. This set now will contain all those elements that are related to x. In our example, this means all objects that are the same shape as x is. And now we have the set of all objects that are the same shape as x. We call this set the equivalence class of x, and we denote it with x bar. Now, of course, this set is the same as the equivalence class of every other element of this set. So, for example, if we have an element y in this equivalence class, then the equivalence class of y is going to be the same as the equivalence class of x. This is because x and y must have the same shape, and the equivalence class of x is the set of all those elements that are the same shape of x, which then of course is the same set as the set of all those objects that are the same shape as y is. Of course, we may create equivalence classes for each object in our original set, and as we've seen earlier, there are some objects that are not related to one another. So we will obtain several different equivalence classes. And now let's look at the collection of all those equivalence classes. This is a set that has as its elements all the individual equivalence classes. So it's a set of sets. And this set of sets that contains all the equivalence classes, all the different equivalence classes of our original set A, we will denote this with A modulo R, which is written with A/R. So A/R or A modulo R is a set of sets that contains all the equivalence classes of our original set A.